All right, here we go. Okay, I'm Austin Griffith. Yeah, you got to do some of this, some of this, some of that. I feel like this is a highly technical talk, so I feel like my silliness needs to fill in a little bit. I don't have as much technical stuff. I'm a lowly application developer, and I try to build things on top of Ethereum. But this is a fun chat where we can kind of get into some of the details of what zkEVM is going to look like and what that's going to look like for an application developer. But first, maybe let's start in on just like some ZK stuff. First, like an introduction, maybe. I'm Austin. How do I pronounce you guys' names? Is it Ye?
Yes. My name is Ye.
Yeah, awesome.
Yeah.
And it was Haichen?
Yeah, Haichen.
Haichen. Okay, awesome. So Ye, Haichen, how's it going? Welcome. Thank you for being here and talking to my caveman brain about ZK stuff. So here's my understanding of zero knowledge. When I try to explain ZK to my 5-year-old, I use the Where's Waldo technique, where there's a big Where's Waldo and there's a big image and he's hidden somewhere in the image. And I can prove to him that I know where it is with a big piece of paper that has a hole in it that I move the hole to show where the Waldo is, but it's covering where the book overall is. So you have a hard time of knowing where Waldo is there, but I can prove to you that I know where Waldo is. And the second analogy is the bouncer at the door of a bar where I have to prove that I'm 21 years old to get in, but I don't want to show him my ID that says my address. So I use a special, I put my ID in a special, so I go up to the door to the bouncer and I put my ID in a special box that is the prover. And that thing prints out a little receipt. And that little receipt isn't the thing that proves it, it's just some numbers. But then I give that receipt to the bouncer and he puts it in his special box, which is the verifier. And out of that box, it says, yes, this guy is 21, without ever having to reveal any of my other information. So you kind of have this prover and verifier, and there's this circuit that both the prover and the verifier are using. And that circuit has some public input and some private input, and then it has some output. And that's the trick, is you can have that private input and the information that happens inside of the circuit is a lot of times like one directional math, like a hash function or something like that, or some kind of proof. That's basically my level of ZK knowledge. I think there's also a little bit of there's zero knowledge stuff that's used for compression, and sometimes there's zero knowledge stuff that's used for privacy. And the roll-up stuff would be like kind of the compression stuff. So that's like where my mushy brain, I think I have like a very, very high level view of this stuff, but would you fill anything in there in terms of the high level view? Is there more to talk about there, or should we expand on that and move forward? What do you guys think?
Yeah, I think those are very excellent examples for like what is zero knowledge proof and how you hide information. But actually, as you mentioned, like there are two functionalities. One is hiding your information, where you prove something, prove that you have this property, like you are under, like you are over 18 or something to a bar or whatever property you have without like reviewing your identity. But another like, huge benefit is that you can also prove this very efficiently. So for example, if I want to prove that my data belong to a very complicated database, so basically you need to, for example, like brute force all the entries. So you need to do a lot of computations there. But what zero knowledge proof can provide you another property that if you have this proof, any verifier can verify this proof succinctly. Even if your initial computation need to execute for maybe days, hours, but your proof verification only takes you milliseconds. So that's why like it can fit very well into this blockchain technology, because blockchain is all about public verifiability, right? Anyone can verify your transaction. So zero knowledge proof can basically compress a lot of things as your security input. They don't necessarily need to be secret, but also like even you don't want this privacy property, you just need to compress a lot of computation into one, and like make this proof become public verifiable, and any node can verify this small proof to instead of re-executing the large computation. So that's how you gain a huge benefit of efficiency, because you are compressing a huge amount of computation into a small proof, and anyone can be the public verifier. And that's
so another analogy, if we use our bouncer at the door analogy and the me with my prover, let's say instead of putting in my ID, I actually put in like thousands of hours of video. And it's thousands of hours of video of me growing up. It's like, here's me at age 1, here's me at age 2, here's me at age 3, all the way till age 21. And basically I put all those years of video into this first prover box, and it prints out that little receipt with like 4 numbers on it.
Exactly,
and then that little receipt can be used by any bouncer at any bar to prove that I have, you know, thousands of hours of video that prove that I have grown up and I actually am 21. Interesting. Okay, cool analogy. Cool.
Exactly.
Awesome.
Yeah, that's a very, very good example for how you can make that both like privacy and also like, you know, efficient, because you have this small, very small receipt to prove a large computation and maybe prove some property during your grow up. Yeah. And so that's actually the key like, you know, key property we use in zkEVM when we are scaling Ethereum, because we only need to compress a lot of transactions, re-execution of those transactions into a smaller proof. So we don't actually need zk property. So that's why like people gave zkEVM another name called validity ROA, because you just need some validity proof to prove something is valid. It's not for zero knowledge proof. And so when people are mentioning like some privacy preserving zkEVM, they might mention like zkEVM, because first zk will be zero knowledge, and the other is abused term for this stickiness. Yeah.
So zk rollup is both compression and privacy is where you start getting that. Okay. So where does so I can see zkEVM fitting in here, where we're just going to do a whole bunch of actions and we're going to feed them into the prover, and then there's going to be this little slip that proves that all of these kind of EVM actions were valid. And then is there then like a challenge period and stuff? Like there's probably so many things to go into, but maybe we should just at a high level, how does the zkEVM come into this?
Yeah. So zkEVM is that you generate a proof from a very high level. We can dive into more detail. Like
we need to be at a high level for me to understand. Let's stay at a high level.
Yeah. So for example, like you can generate one proof. So basically, assuming that you are application developer, right? And users like are interacting with your smart contract. So users send some transactions, and like after some Ethereum node receive these transactions through some like RPC interface, or so it need to re-execute this transaction like on a guest node, right? Let's assume we just use Go Ethereum as our node implementation, and so this transaction will be parsed, interpreted into some EVM bytecode. It will execute opcode by opcode to execute the smart contract logic, right? And so initially on layer 1, every node need to re-execute this transaction to move from state 1 to state 2. And that's a security guarantee you get from the decentralization, because there are so many nodes re-executing the same transaction to move from the same state 1 to same state 2. But the problem is that such re-execution is inefficient. And because everyone need to, you know, redundantly re-execute that. So what zkEVM can do is that instead of re-executing all the transaction, you hide that all behind the door. So basically you receive, for example, 10 smart contract transactions, and initially you should execute that on EVM. But instead you generate one distinct proof to prove that those 10 transactions are executed correctly on Ethereum virtual machine, like to move from state 1 to state 2. So from a high level, the public input for zkEVM should be your transactions, maybe 10 like smart contract transactions, and your old state, and also your new state after executing the transaction. And the proof will prove that applying those 10 transactions to state 1, you will get state 2. And then like you send this proof with some necessary data like to Ethereum layer 1, and then every node need to verify this proof and know that, oh, it's moved correctly from state 1 to state 2 without re-executing. And because it's a lot cheaper, so that's why you can be more efficient and how like this scaling work. And as far as you mentioned like some challenging period, so basically optimism or optimistic rollup in general, how they are doing that is that they directly post state 1 and state 2 on chain and waiting for anyone to challenge whether there are some if you post some incorrect new state, right? So what zkEVM can provide you is that as far as you can provide this new state root with a proof and it's verified to be correct, then like there is no chance.
So there's no challenge because it's verified.
Yes.
Okay.
Yes. But the latency comes from like you need some latency to generate the proof, right?
Because the verification.
Computational. Yeah. And so that's why like you still have some like, wait for some time for withdrawing from layer 2 to layer 1, because you need to generate this validated proof and wait for verification on layer 1.
So, okay, so let me make sure I understand that. So right now, the current state of operating is I have my Ethereum node right here. And anytime anybody makes a transaction to a smart contract to update some value, every one of the nodes all across the network run those transactions in a raw opcode way. But in this case, we're taking all that stuff that runs and we're running it in our own black box verifier, and we're printing out that receipt again. And instead we're sending the receipt across the network, the numbers that prove things. And basically anybody can take their prover box and put the receipt in and prove that that transaction works without having to run through all the verification of it. So it seems like this verification that's happening, is that happening on the client side, or is there like some verifier that you have to go to? Is it computationally intense? Like, does the verification process create centralization? I guess might be a question.
Yeah. So I think there are some like slightly terminology.
Oh yeah, maybe I'm using them wrong too. Yeah, sorry.
Yeah. So when you are generating this proof, it's actually a centralized large prover thing. Like for example, like I'm running a large layer 2 node and I receive all the transactions and I run some proving algorithm to generate this small receipt. So that's on the prover side. But anyone on the Ethereum node will be the verifier, because this
the verifying is easy. Right. But the proving is hard.
Yes, and verifier need to be run by everyone, because it's actually encoded. This verification logic is encoded on smart contract. So you need to verify that on smart contract. So basically everyone need to verify this, and verify is cheap, proving it hard.
A centralized prover is not really that big of a deal. It's the part that needs to be decentralized is the verifying, and everyone needs to verify easy. It's not that big of a deal if you send it to a centralized prover to get your receipt back, because it's the receipt and it's getting the receipt to everyone else and having them verify it. That's the important part. This prover could go down and someone else could spin up another one. And it's more of like it's a point of failure, but it's not a point of centralization. I don't know. I think I'm understanding what you're saying though. It's like the proving can be on a big machine or a set of big machines, but the verifying needs to be decentralized, and every node on the network, everyone at home needs to be able to verify. But that's a quick and easy process thanks to ZK proofs.
Yes, exactly. Cool. That's correct. And
okay, cool. Yeah, I think I understand from a very high level. As we get into this, maybe good questions might be, what will change for me as an application developer? Or maybe even like, what are some of the assumptions or new things that this unlocks as an application developer? Can I make games that have some bits of privacy to them? Can I make games that have faster speed? Like what when it comes down to it, when we have the zkEVM implementation live and people can be hitting this, what's the difference for an application developer?
I think Haichen can talk more about on the concrete deployment side and what were changes, and I can talk more about on the application side. So one thing like you can benefit on layer 2 is that you get some more instant pre-confirmation, because you are running a centralized proving node. All the transaction will be sent to a centralized node. So you will get some much faster pre-confirmation, like for one block generation time. Like as far as your transaction included, I will send you some pre-confirmation so that you know it's already included there. So you get better UI and UX. And also another benefit you get is that you can inherit this security and decentralization from Ethereum, because everyone is verifying your receipt, and because it's equivalent to re-executing the transaction. So that's why like you get this decentralization and security guarantee. So that's all like for the application. So basically you can do some more crazy stuff with lower gas fee and with a better like pre-confirmation within layer 2. And Haichen can maybe talk
speed so far. So the first thing is, since we can go to a centralized prover that can prove a whole bunch of complex actions and give me that nice little receipt back that I can send to anyone across the network and they can verify it. And first of all, I can verify it myself quickly. I can get the receipt, verify it, make sure it works in a verifier, and then share it with everyone else. So because of that, I get just like fast, it's like network bound basically. Like there's some compute bound on your side, but it's mostly network bound, and then you guys will scale your compute to handle it. So it's
Yes.
mostly network bound transactions instead of waiting for proof of stake or proof of work to happen every 15 seconds. I
Yes.
fire a network command and I get a receipt back from you guys, and that receipt can be quickly verified by anyone. So first of all, just quick and just fast, right? Okay,
Yes.
cool. And
Yeah.
cheap.
Also,
Yeah, go ahead. Yes, please.
yeah. Also, I want to add in like a little bit like on the finality stuff like that. So if you look at our testnet, so currently we have 3 different levels of the finality. So first of all, like it's pre-committed, which means like a block is included inside the layer 2 blockchain, meaning like you send a transaction like RPC request to us, and then we say, okay, now this transaction has been accepted and also included in the layer 2 block and sealed in a layer 2 block. Then we call it like a pre-commit. Yeah, pre-committed. Okay. So that means like it's only included in the layer 2, and then because like we're running like centralized node right now.
But that comes back right away.
Yeah, that comes back like can be very fast, like and then faster than the layer 1s. And then the second layer state we call like it's committed state. So where committed state is we roll up the transaction data to the layer 1. That means like anyone who like want to, they can reproduce basically a layer 2 blocks with that transaction data. So that means like it has a more confidence that this block was included, and then you can replay this transaction and then know, okay, you get the same state root like as we uploaded to the layer 1. And then the third state will be the finalized, which means like that you already using the zkEVM to generate a validity proof, and then you upload this validity proof to the layer 1, and then being verified by a verifier smart contract there. And then that means like all the transaction within that block is finalized and then sealed, like no one can change that. It's definitely corrected, execute on the layer 2, and then you don't need to really like to using the transaction data to reproduce the block yourself to be sure that your transaction is correctly executed on the layer 2.
So let me make sure I understand that. We have like 3 levels of how committed and how solid your transaction is. I make a transaction I want to make a transaction on a smart contract. Basically, I send that to your verifier and I get the pre-commit back almost immediately. It's like network bound. I send my transaction, I get back a pre-commit that says that it's in. Then it's written on the L2, and then it's written on the L1. And those are kind of the 3 layers. Okay, cool. Okay. Just from a high level. That's a high level. So where can things go wrong? Let's say I make a transaction on a smart contract and I get the pre-commit back. Can something break along the way where that pre-commit isn't good? Or is it basically, as the application developer, as soon as I get the pre-commit back and it proves and it verifies correctly, I'm assuming that everything else down that line of down the chain, it will get committed? Can things fall apart there? Like, what can happen there as okay, let's say it's a lottery and I just made the transaction that generated my random number somehow, and I'm about to pay out the person. Do I need to wait? At what point do I make the transaction that pays the person out, and how can they like grief the game or something like that? Just trying to think of this from an application layer development kind of standpoint.
Yeah, I think that's a great question. So I feel like I think like that there are different level of confidence like there. So usually once you get pre-committed, you just know like in the future you will be committed on the layer 2 on the layer 1. So that's like if you trust us, and then you can think like if it's pre-committed, then the transaction it should be like included in the future, and then the data will be uploaded that. And then but if say like you're making a very important transaction, you don't like want to trust us, and then you just like want to wait. So one thing is like you can do is you can wait until we roll up the data into layer 1, and then you can run a node like yourself, like a sequencer node. They just follow up like on all of the data you uploaded to the transaction on the layer 1, and then at that point, you can re-execute like that transaction on the locally, and then see if you get the same state root. If that's right, you can get like a faster finality, and then you can if it's not in a rush like for your need, and then you can just change to the you can wait for the final. You don't want to re-execute the transaction yourself at a local node, or if it's a mobile phone, won't be able to do that. Then you can just wait a little bit longer until that validity proof has been generated and uploaded and verified on the layer 1. At that point, I guess all the transactions definitely can be sealed, and then no one can change that or touch that anymore. And then in that case, like you don't need to trust us, and you don't need to re-execute them. You just like wait for the validity proof.
Yeah. So what kind of time are we? So pre-commit is probably like almost network bound and a little CPU bound. And then the finalization on the L2, how long does that take? And then finalization on the L1, how long does that take?
Yeah, for the data availability, like so for the committed state, you probably wait like a little bit longer, probably like almost like a 1 minute, and then you can just wait for like and then commit like the data into the layer one. For the finalized,
you're committing to L1 at least like every couple of minutes. Is that right?
Yeah.
Okay.
Yeah.
Sorry to interrupt.
That's right. No, it's totally okay. Like to clarify things, and then for the final like validity proof, currently it take about 15 minutes to finalize. 15 to like the 30 minutes to finalize a state like and to generate a proof for that. And now somehow like it's also depending on like how much proving power we have like in the network. But like in the future, like for example, if we launch like in the like a far future, like in a year, we think like if we have enough improving power, so like that time will be like within an hour. So usually like you can just that like a proof can be generated like around like the 15 to 30 minutes, and then you can just sending that proof to the layer one, and that will be verified out there.
So if you had some very, very, very sensitive stuff and you had millions and millions of dollars you were about to pay out, you could set it to kind of close the lottery, get the random number, and then maybe wait even an hour before you do the finalize and payout, just in case someone's griefing the system somehow. Okay, cool. So you're writing to the L2 every minute, or you're writing to the L1? I don't understand how you're writing to the L1 every couple of minutes, but you still want to wait for an hour of finality there. Maybe that's too far in the weeds to talk about, but if maybe you could hit it at a high level or explain it at a high level.
Yeah, so first of all, like every like a few seconds, you can generate a layer 2 block, right? You accept a few transactions and pack them into a block. And then you can do like what you can do is like you can just getting those transaction data and then sending that to the layer 1. So everyone can download that block. And then also like transaction data, once it's written in the layer 1, so you cannot change in the layer 2, right? So because you already sending, okay, after applying these transactions with those transaction call data, which we will switch from the original state root to a new state root. That's like the written on the layer 1.
So
no
it's
one can
transaction
change that.
data versus transitioning to a new state root, and it's transitioning to a new state root that takes that half an hour time, but transaction data is hitting mainnet pretty quickly. Within a couple of minutes your transaction lives on mainnet, but it's not there's not a straight state transition to a new root, except for like maybe every half an hour or an hour or something like that, which then like bundles everything up and gives you one state root on chain that's like fully validated. Okay, cool. I think I understand.
And then also like adding just one more point is those transactions that will actually be used as a public input to verify your proof. Because like you cannot say like I hidden everything like as a private input, then I just like verifying like all those transactions. So you're never sure like you're using the same transaction data you use like inside proof. So those transaction data will roll up like in the previous states. You will be used as a public input to verifying your proof. Okay, you're actually taking those transaction data and then using to verify the proof, and then making sure like the state root is transition to the correct new one.
So from a high level, let me make sure so there's this circuit, right? There's this circuit that does the proof, and the circuit has a handful of different inputs, and one of the most important inputs to the circuit is the previous state of the whole block, and that's very public, and everyone has that, and that's it's key that everyone has that to be able to do their verification. They have a very public previous state root, and you put in the previous state root and then whatever new transactions you have at the same time, and then out of that comes a new state root, and that's okay. Making sure I understand that. Cool.
Yeah, that's correct. Yeah.
Awesome. Okay, so let's see. As a new developer, it's going to be similar to other L2s or even side chains. For me, I connect to an RPC, and it's just like my transactions happen faster, basically. but everything is pretty EVM compatible. I remember the difference between Optimism and Arbitrum. Gas was a little bit different. Like the gas limit when I deployed to Arbitrum had to be a lot higher for some reason, but I ended up paying about the same amount. Will things like gas limit and gas prices be things that we need to worry about or think about as we're interfacing with the zkEVM?
Yeah, we may like we'll tweak a little bit on the gas cost for like the different offcodes. For example, certain like offcodes, it's fairly cheap to execute them, but if you want to verify them in the zkEVM, then it could be like a lot more expensive. So we maybe like to make a little bit small tweak to certain a few opcodes, but like in general, it will be like staying the same as like the overall like the gas cost model for every opcode you have. So it's just like to prevent anyone like to trying to DDoS like the network. So you're just using those very cheap opcodes with gas cost, and it will just generating like you spending a lot of cost to the zkEVM, and then basically that would be blocking the network, like how many transactions can include it inside a single circuit.
So in a normal EVM, with all of us having our nodes here, anytime you store something, it's very, very expensive because all the nodes on the network have to store that thing. But what's expensive in this situation is the proving of the thing. And that prover is the CPU bound piece that you guys have to spin up. So what's an example of an opcode that's difficult to prove? Maybe that's too in the weeds, but maybe we could get an example of just like, storage is really expensive over here, but what's really hard to prove? Is it some mathematics stuff, or is it like, what is it?
Yeah, so for example, like one example is the cat check opcode, the SHA-3
okay,
opcode.
So
that's like
function.
the hash function. So that's like using a lot of the bitwise operations, and that would be very expensive to prove that inside the ZK circuit.
Got it. And you also mentioned that your network has more proving capabilities. Now, at first, that would just be your centralized prover is spinning up. But it sounds like you're going to maybe even decentralize the proving, and other people will be incentivized to run their own provers, and people could hit someone else's prover and get an example back. Is that, am I thinking about that right?
Yeah,
right?
I think
okay.
Yeah, that's correct. So the thing, like the idea behind it is that you can generate the blocks very fast at a very fast pace, and then you can like keep like a few like a recent blocks open like for generating the proof, and then all the proof generation can happen like in parallel, and then all of different different parties, different community can run their own prover node, and then to get some task job like that we distributed from the network, and then say, okay, you are going to prove the block number 100, and you are going to prove for the block 101. And then you once you like both getting like those proof generated, and then sending out like the proof, and then you will get some rewarded and incentivized to generating the proof. And then so with like the decentralized proving network, we believe like we can have like a massive we can support a lot of the throughput, and then we can also have all of the community participating in our network.
And the trick there is just providing the correct like incentives for folks and creating it so other people can run it. Okay, very cool. So at a high level, as an application developer, I'm going to be going to an RPC. I'm going to be sending and receiving transactions like normal. I'll be deploying smart contracts. The gas will be a little bit different based on how expensive it is to prove, not how expensive it is on the EVM, but it'll be very similar to that. It's not private. The stuff that I'm putting in here, it eventually lands on chain and is public, but it's fast and cheap and easy for me as a developer, and that's the key. So it's still public, but it's what the ZK we're doing here is compression, and we're getting it so you can do lots of things over on this L2, and then that will now and then get verified with a state root on the L1. But it's just fast and cheaper over on the L2. I think I understand most of it, but I mean, like from a very high level, of course. What are maybe some other gotchas? Things like randomness, or things like what are some of the other like gotchas with account abstraction? Anything like that you guys do differently? In terms of how randomness works, or how account abstraction works, or anything like that? Or is it strictly like EVM, it's going to work exactly like your EVM network works that you're used to?
So right now, actually, we're just working as like exactly what EVM looks like.
Okay.
So,
which makes sense.
But we actually, we first I want to make sure like we're being compatible for most of our wallet, like MetaMask or other like wallet you're going to use, and then so you get like same functionality. But actually, we're also like looking to active researching about like the account abstractions, and I think like that we all believe that will be like a future. So you feel like it can support all like flexibility to those account, and then we're just looking into that, and then we will support like and then like rolling out like the new research like the results there.
Cool, awesome. So as a developer, it's easier if I just think of it as it's exactly the EVM. It's just going to be faster. and probably cheaper. And just think of it like it's the EVM, but faster and cheaper, and let you guys handle all the details in there. And basically step one is getting it to work. And step two is getting it to work and having that prover be more decentralized or something like that. I'm assuming it's still decentralized, like you guys said, because the verification is decentralized. And that's what's key is, even though this node is getting every transaction, it can quickly verify it, but it has to run through everything. But the EVM is so simple that that's okay. But at a high level, at like an L2 level kind of bandwidth, it wouldn't be able to keep up with that. And that's where the ZK proofs come in and make it easier. I don't even know where I'm going with that. Just kind of down the what else should we talk about? What else should we cover? What are some other blind spots that we have, even from a high level still?
Yeah, I think that's mostly like from the high level, like, you know, the theoretical knowledge side. And
okay.
Yeah.
So as a builder, yeah, as a builder, great. That's woo, we did it. Yeah, you can tell like at my knowledge, like I only have just enough. So as a builder though, I can just think of this as a new network. I'm just going to talk to it on an RPC. I might have to tinker a little bit with my gas limits and gas prices, but that'll be probably somehow built in or somehow pretty automatic for me. You have to know going into it, is this a privacy preserving thing, or is this a compression thing? This is more of the compression side. So I know that my transactions will still be public. So don't assume anything's private there. But I think these are the concerns that I have as a builder is, will my tools work with it? As long as it's EVM compatible, it sounds like yes. And then what the assumptions are about cost and gas and time. But I think we've covered almost all of that stuff. So basically, I think if you guys gave me an RPC endpoint, at this point, I'd be able to understand what I'm talking to and understand what I should expect and be able to just make transactions on it. Thankfully, because you're making it EVM compatible, then all my other stuff just plays with it normally. So I think that like as a builder, I think I understand everything here. And I think that if you released an RPC, I'd be able to start talking to it and tinkering with it. Are there extra tools? Maybe like the verifier needs to be a new tool that I need to learn how to use, or are there just new concepts that we didn't cover? It sounds like we've covered most of this stuff from a very high level, obviously, but can you think of any other things for an application developer that I should go research or I should learn more about to prepare myself to be able to build apps on zkEVMs?
I think like one point is like we're trying to hide everything complexity behind that. So like from the developer this point of view, like you don't need to know about like a verifier, about like ZK proof. You just need to know like what you're working on. Like you just know solidity and how to deploy your contract. That should be enough. And then, but like if you want to like, for example, to do debugging, and then like once you know about how the states, those status of different commit level of that, we have like developing some front-end website to show up like what's the current status of the block. Is it like it's currently stay as the pre-committed, committed, or like finalized state, and it's showing that like actual information to the users and then to the developers to see like how is the transaction and how's everything like that in the current status, because that's kind of the actual things like the new to the L2 than the L1. So in the layer one, you just see like everything, like if it's included, and you can find that in the EtherScan, like in the block explorer, then that things should be good. The probably only thing you need to wait is like how many extra blocks like the to confirmation you have for that. But for layer two, it could be like slightly different because you need to do the roll up stuff. Like the roll up status will be like a new things like to the developers and to the users.
It's interesting. Yeah. So even though EVM compatible, a lot of the tools work, but since there are a handful of like very new things that you guys are working on and trying to keep that abstracted, there's going to be new interfaces. There's going to be a new EtherScan for this that's going to be able to tell me in more detail about that pre-commit and what stage it's in, and as we get committed and how many blocks deep it is. Interesting. Okay. And are you guys building most of that? Are you trying to find a community to help build a lot of that stuff? Like, what's the roadmap for some things like an EtherScan that shows this kind of stuff on L2?
Yeah, for the EtherScan, I think we're collaborating with like their team, and then we're just also collaborating with other community members to build like things and then to make sure like all of experience. And then we're also trying to to collaborate with community as much as possible. Initially, we maybe build some temporary solution to show up extra informations, but on the road that we were just working with the community and then to integrate with all of their tool set and then their interfaces, and then we just don't change a lot to the user experience and developer experience.
Awesome. Usually when I talk to L2s as an application developer, as I'm thinking about how to build on an L2, I always try to think about what is the technology that makes it different than everyone else, and how can I show that off? If it's if it's an EVM if it's an L2 that does high computational stuff, then I want to do a whole game of life simulation that can all happen in a heavy compute and then come down to a single proof that it did end up at a certain state or something like that. Is that where, would you say that those are the kind of applications that you'll see deployed here? Of course, since it's EVM compatible, everyone will be deploying all their NFTs and everything else here. But is there a specific application use case that works really well in your zkEVM that would be, that if someone built it, it would be a good display of the EVM and showing the capabilities?
Yeah, I think that's also that's a great question. It's what type of application. So actually, in general, we just want to support every application that people are working on and people are excited about. So I think so those applications which requires a very high frequent transactions, high frequency transactions. Yeah, like a game, or a social apps, and then but they both requires a lot of the transaction throughput. And then, but with the low cost, those kind of applications I think will be very good, on the zk. And then, but also in some sense, the DeFi also sometimes if the transaction fee is too high, then it will just stop some normal users and retail users to play with that because of transaction fees. And those DeFi applications, they also requires very strong security guarantee. So those will be also very suitable for the zk, since the zk is built to be secure and then inherit a security from the Ethereum itself.
Great, that makes sense. So it's more I feel like Ethereum is moving more and more toward mainstream audiences as we implement these new kind of layers where things are cheaper and faster. And on L1, it's expensive and it's slow, but it's very secure. And then as we have these L2s, they can be just as secure because they settle to the L1, but we can have faster, quicker transactions. I've heard of, and the best application for that is something like games and social apps, but you can run all your other EVM compatible stuff here and it will work the same. But this will unlock new powers where you can have quick and fast transactions like a game or a social app. I've seen people, I've seen people building EVM games right now, and they're building them in rollups on a side chain. So very, very, very cheap. Is there another level here that goes even farther, where we have L1 settling, we have L2 kind of rolling up a lot of information? Is there an L3 that leads to basically real mainstream apps? If we think of Facebook right now, and we think of all the interactions that are happening on Facebook, that can't even work on L2, right? Do you foresee farther abstractions here, or what do you guys think will happen in the future?
Yeah, I think that makes total sense. So I think if you directly compare with our layer 2 with a sidechain, I think the biggest guarantee is still we inherit the security and decentralization from layer 1. So because my prediction for the gas fees on our layer 2 will still be a little higher than sidechain, because that's what you pay for security, right? Because you still need to post your data on Ethereum. If you want to, you accept that you can post your data, your transaction data on another data availability layer or something like that, you can be cheaper than sidechain. But if you still post your transaction data on Ethereum and following this standard zk rollup diagram, you have to, it's still more expensive than sidechain. But if you build something on top of layer 2, as you mentioned, layer 3, you open even more possibilities. For example, if our layer 2 is zkEVM based, so which means a EVM compatible, EVM equivalent layer, it supports Solidity and everything that's running on EVM. But on layer 3, you have more flexibility. You can have different choice of VM models you are running, as far as you verify your proofs on layer 2 cheaply. And also you can, you get a lot of self-control over this layer 3. You can use any SDK and anything like you want to use. So I believe that in the future, L3 will be more suitable for, especially for certain applications over sidechain, because it can offer a higher security guarantee. And
that was my question.
Yeah.
Basically we're just waiting for the technology to be there. But these folks that are deploying mainstream like applications over on side chains or over on rollups on side chains will eventually move into this L2 or L3 world because of the security guarantees that you don't get that with a side chain. Yeah, that's what I was wondering, is like eventually this is going to be the right environment for those folks, and they'll be deploying those same games, but those same games will now have the security benefits of L1 Ethereum. Yeah.
Yes, exactly.
Cool. Awesome. I think I'm like, honestly, as a developer, I think that since you guys are doing all the work to make an EVM equivalent or compatible, as a developer, I don't really need to know that much. I need to know some of the high level stuff, like, is this private or not? And what is this thing doing that's really good? And maybe even like, where are the centralization points now, and how can that be more decentralized in the future? But we've already covered those questions, I think, on this call. I think I understand most of them from a very high level, of course. But yeah, anything else that we should cover? Basically, if you gave me an RPC endpoint and sent me some money to one of my addresses, I think I would be off to the races, and I'd be able to build things. Is there anything else that would stop that, or any concerns you'd have? Or should a developer just be watching for that RPC endpoint to come out in the future?
Yeah, I think like so developers can just waiting for like the RPC endpoint, and we just like will support the contract developer very soon. So another thing, like one point we want to add is like currently the sequencer, all of the block generations, like L2 block generation, is centralized, but we also have the roadmap to make that decentralized as well. Like in the future, everything will be decentralized on the scroll. And then that makes like the pre-committed even like more, given more confidence to pre-committed, because it will be pre-committed to probably like a few blocks and then a few sequences, and they will be like kind of running a small POS in the future, that giving like the pre-committed state or even like more confidence to do that. And then also removing like the trust and then from like the central entity like from us.
Great. Just like knowing that that's on the roadmap is important, I think, for a builder to know that, like, yes, it'll be cheap and fast right now, but there's some implications there of centralization. Of course, the verifying is still decentralized, and that's what key, but the proving needs to be decentralized eventually. And if a builder's thinking about building on one of these different zkEVMs, they're going to have questions about which one is going to be, most decentralized in the future or most popular in the future. So that comes up. Other questions for a builder might be like bridges. Is there anything interested in about bridging in, or will that all work the same way as other L2s? Sorry, I think maybe you were going to say something first.
Oh, no, it's just,
we can talk about bridges second if you've got something first.
Okay. Yeah, just because you quickly mentioned, like, there are different zkEVMs, and so we are only talking about what this this zkEVM version we are building with the privacy and scaling exploration team at Ye Foundation. It's called a community version because it's built totally in the open source way.
Cool.
And so, but there are still some other zkEVM implementations. But so far, we are the most closest to the Ethereum implementation. First, our sequencer node. So as you mentioned, like when you're sending RPC request to this node, our node is directly a fork of gas. But other implementations are not. It's not necessarily exactly the same environment as the gas. So for example, like they might build their own executor and build their own interpret logic to after receiving this transaction and generate proof for this, their own logic, their own execution logic. But we are so far the only one which directly using a fork of gas, which makes that lower level compatible and make especially developer become more comfortable, because it's not only the RPC interface will be the same, but also the interpreting logic will be the same. And also another interesting feature is that we are like, there are different terms, especially in terms of zkEVM. They are like sometimes called EVM, like bytecode equivalent. There is language compatible. There is a lot of terms, and I can like elaborate a little bit more, like how that differs from the applications level developer. So we are building something called bytecode level like equivalence, which means like all the EVM, we are directly proving for the initial EVM opcode execution, opcode by opcode. But there are some constructions where you can only be compatible with Solidity because you build a different virtual machine and you need some different compiler to compile your Solidity to this virtual machine. So from developer perspective, they can still be language compatible because you can use Solidity, but it's compiling to a different target VM and different executor. So that's something like which make that difference. So that's why like people, I think Vitalik also classified that into different types, where it's language compatible, bytecode level compatible, and they eventually become Ethereum equivalent because your implementation will be exactly like current Ethereum. So that's 3 different levels. And also like that's also a very interesting trade-off due to the proving cost, because as we discussed earlier, SHA-3 and catch-hack, those type of hash are very expensive when you're proving. But there is one type of hash function which is really easy to prove. Like for example, you just replace this hash with Poseidon hash
or something like that. I see
yes,
MIMC a lot. Yeah.
Yes,
yep.
yes, and those the proving overhead for MIMC compared with catch-hack can be 100 smaller. So that's why like people are pursuing for zk friendly hash function, but they sometimes break the the compatibility. For example, you need Cre2 to compute some address, and you need to do something like that. So that's the trade-off between a proving overhead more compatible, or you want a more efficient prover. So yeah, that's something like I want to
and
add,
there's
like,
nothing
on the comparison that
there's nothing I can do on the application developer side. All I have is catch-hack, and I can just use catch-hack, but that's going to be expensive to prove.
Yes.
Are there other like pre-compiles coming into the EVM eventually that might be more MIMC friendly, or is that not even a thing?
Currently we want to support the initial pre-compiles as some sub-circuits. Like we just build some specialized parts to prove for those pre-compiles, because pre-compile is usually very expensive, like pairing and those stuff. But we plan to support that more.
Cool, awesome, great stuff. And yeah, I'm guessing bridges, going on to the bridges will work the same way too eventually. Like you'll be able to, again, I like how we like zoom in and talk about something kind of cool, and then zoom way back out to the caveman developer who's like, I just need to get an RPC and some ETH so I can deploy. And I think all of that stuff will work the same, right? Bridges will work the same. The RPC endpoint will work the same. Gas might be a little bit different because certain things are a little bit different in terms of proving cost, but that will be built into the network and will be probably pretty agnostic to me as a developer. I'll just make the RPC calls I need, I think. Is that right?
Yeah,
you guys will handle all the complexity beneath the abstraction. Yeah.
So, and then also talking a little bit like more about the bridge. So like the bridge, like there are 2 ways. Like one way is like deposit from the layer 1 to the layer 2. That would be like work as similar as like the other existing bridges. Like you just wait for a few confirmations on the layer 1, then the fund will be actually like the funded on the layer 2 wallet. And then the exit will be a little bit different. So the exit is like for the bridges, like you're just waiting for the proof the block to be finalized, and then like
that's and then all of the block hash gets written. Okay.
Yeah, like
so it's not the 1 minute thing. It could be a half an hour or an hour.
Yeah,
but then that hash gets written and the funds get bridged. So the bridges on the exit will need to wait for that state root to get written. Is that right?
Yes.
Okay.
Wait for the state root to get it written and then being verified by the validity proof.
Okay. Which is still only like an hour. Like some of these roll-up solutions for fungible assets, they create a market around them so you can exit quickly, but it's still there's like a week-long challenge period on some of these, right? There's no challenge here, there's no game being played. It's all it's verified by the prover in the first place, and anyone can verify it with the verifier. Okay. Cool.
Yeah, that's right. That's the point of the zk rollup, is trying to reduce the whole like the bridging, like exit time, like avoid this 1 week challenging time, just using the mass, like prove the mass secure the zk proof to do that.
Awesome. Okay, I think my last question, I think I've already asked it, and I think I've already gotten the answer. I'm always looking for what's something unique that I could build here that I can't build anywhere else? And we talked about like just mainstream apps. It's going to be faster. It's going to be cheaper. Are there any secret moves or secret things I can do on this network that I can't do in other places? Or do you guys perceive any kind of specific applications being run here that wouldn't run anywhere else? Or is it mostly about it's all the EVM stuff? And the most important thing is just making sure we have that full compatibility and all the stuff you can do on EVM, you can do here. Or is it all of that plus there's some secret moves that you can do?
I think right now we're just being EVM equivalent.
EVM,
So like you can
good.
be like,
Well, that's great.
Yeah,
that's hard enough as it is.
Yeah.
For sure. Yep. Yep.
Yeah. Then like
Okay.
our first step, and then but like more fun stuff will be coming later.
Okay. Is there, I mean, like what kind of, like, it's not like something that's not like a promise on the roadmap or anything, but just from a high level, just so I understand, what kind of interesting things can be built into these in the future?
Yeah, so some sorts like in our mind, like it's, for example, we can support some new precompiles or some even something like new, like which will be further reduce the cost of the whole like transactions. Like for example, put some very useful, like a very common use cases like into some precompiles, and then you have a specialized circuit for that can further reduce the cost of those transactions. And then that would be like some interesting things like to explore.
Awesome, cool. Yeah, and it'll depend on the circuit. I noticed when I was
I think
sorry, go ahead. You got it. Hit it. Let's go.
Yeah, I mean, it just as we discussed earlier, like it will open, your imagination to build layer 3 and use any type of SDK. Because as a layer 2, we still think it's still a base layer. Although like layer 1 is settlement layer, layer 2 is execution layer, layer 3 maybe for imagination. Like you can use any type of VM, and you can use more like zk friendly virtual machine, and then but verifier proofs on our layer 2, and then you still inherit the security from. But I think layer 2 is still built for security, inherited decentralization, and with a cheaper gas cost. So yeah.
Yep. Awesome. Yeah, I think it's for building mainstream apps. I mean, or it's maybe the stepping stone that will lead us to building mainstream apps. And these apps will be somewhere in between mainstream and the current EVM stuff, and it will lead to kind of the next step of mainstream apps. I think that's a cool way to put it. Awesome. So, okay, what about any, we probably better dip. Oh, actually we're right at time, huh? You guys got to go. My last question might be, is there any kind of zk that you guys are thinking about when we talk about privacy preserving stuff? Is there any future roadmap of privacy preserving stuff within the scroll architecture?
Yeah, I think as far as we can support cheaper proof verification on our layer 2, then we can definitely support like zk and especially zk, like novel zk applications on layer 2, because we can verify their proofs or have a better compatibility model to interact with those applications. So that's our plan. Like, as a base layer, we just want to make sure that all the functionalities are working correctly and cheap, and also like build some, cheaper proof verification to support, those zk applications built on top of us and things like that.
Awesome. Great. All right, Ye, Haichen, thank you guys so much. This is awesome. I learned a bunch already. I have a lot more to learn, but I think from an application layer, you guys are doing all the work for me. I just need to deploy things and use the same tools I'm already using. I'm just waiting for it to be available, and then I can start deploying stuff. Thank you guys for being here, and thank you guys for letting me know.
Yeah, thank you for having us. Yeah. It's like a very fun, interesting session.
It's fun to talk about it at a high level and ask stupid questions. I've got a lot of stupid questions. Thank you guys very much. Awesome. All right, thanks. See you guys.